Welcome to Cell-Based Maths Capsule. In the last session, we defined what a fieldless tension is. What is the importance of these fieldless tensions? We see this importance via Kronecker's theorem. The statement of the Kronecker's theorem is as follows. Let f be a field and fx be a non-constant polynomial over f. Then you can always find a extension k of f and an alpha in k with f of alpha is equal to 0. That means that if fx is a non-constant polynomial over f, then you can find an extension k over which fx has a root. Let us see the proof of this. So because you know that fx is a u of t, any polynomial can be written as the product of irreducible polynomial over f. So fx also can be written as the product of irreducible polynomial over f. So let p of x be an irreducible factor of fx. So because fx is a PID and px is an irreducible polynomial, the ideal generated by p of x is a maximal ideal. Therefore, the quotient ring k is equal to fx mod p of x. The ideal generated by p of x is a field. So we show that this f can be identified with the subfield of this field k. For this, we define a map phi from f to fx mod p of x, which states a goes to a plus ideal generated by p of x, where a is in f. So we first show that phi is 1, 1. So suppose phi of a is equal to phi of b. That means by definition a plus ideal generated by p of x is equal to b plus ideal generated by p of x, where a and b are in f. So the difference a minus b belongs to the ideal generated by p of x. That means that a minus b is a multiple of p of x, or p of x divides a minus b. But by assumption p of x is an irreducible polynomial, so its degree is greater than 1, greater than or equal to 1. And because a and b are in f, a minus b is also in f, and therefore the degree of a minus b as a polynomial over f is equal to 0. So p of x divides a minus b means, and the degree of a minus b is 0, which is possible only if a minus b is equal to 0. That means a is equal to b. So hence phi is 1, 1. Clearly phi is a ring homomorphism, and therefore this phi maps f onto a subfield of fx mod p of x. So we identify this subfield by f. So what is that subfield? Which is the set of all a plus ideal generated by px, where a belongs to f. So we identify f with the subfield. Therefore we can view k as an extension of f. So we now show that k contains a 0 of p of x. So let alpha is equal to x plus ideal generated by p of x, then alpha is in k. So if p of x is a polynomial of degree n, then p of x is of the form a0 plus a1x plus and so on an h raised to n, where ai belongs to f. Therefore p of alpha is equal to a0 into 1 plus ideal generated by p of x plus a1 into x plus p of x plus and so on an into x plus ideal generated by p of x the whole raised to n. This we can write as, using the addition operation and multiplication operation in the quotient ring, we can write this one as a0 plus a1x plus and so on an h raised to n plus ideal generated by p of x, which is same as p of x plus the ideal generated by p of x, which is equal to the ideal generated by p of x, because p of x belongs to this ideal, and which is same as the 0 in k. That means that p of alpha is equal to 0 in k. Because p of x is a factor of f of x, the roots of p of x are same as the roots of f of x, are also a root of f of x. Therefore f of alpha is equal to 0 in k. Therefore fx has a root in k. Now, what are the elements of this field k, which is same as fx mod ideal generated by p of x, and what is the degree of extension of k over f? So let us see a theorem which state the following. Let p of x belongs to fx be an irreducible polynomial of degree n over a field f, and k is equal to fx mod the idea generated by p of x, which is a field. Let theta is equal to x plus idea generated by p of x, definitely which is an element of k. Then we can show that the elements 1, theta, theta square and so on, theta raised to n minus 1 forms a basis of k as a vector space over f. So, and therefore we can write any element of k as a linear combination of 1, theta, theta square and so on, theta raised to n minus 1, or k is equal to set of all a0 plus a1 theta plus and so on an minus 1 theta raised to n minus 1, where a is r belongs to f. So let us see the proof of this. So let us take one element in k. So let alpha belongs to k. So then k is equal to fx mod p of x. So alpha will be look like ax plus the idea generated by p of x, where ax belongs to fx. Because fx is an Euclidean domain, by division algorithm, there exists a qx and rx belongs to fx such that ax is equal to qx into px plus rx, where rx is equal to 0 or degree of rx is less than n. So therefore alpha you can write it as, which is same as ax plus idea generated by p of x, but ax is equal to qx into px plus rx. So we can write alpha is equal to qx px plus rx plus the idea generated by p of x, because qx into px is an element of the ideal. So qx px plus the idea generated by p of x is same as the idea generated by p of x. So alpha will be rx plus idea generated by p of x. So because degree of rx is less than n, let us assume that rx is equal to b0 plus b1h plus and so on bn minus 1 h raised to n minus 1 for some bi belongs to f. Then by above expression, alpha is equal to rx plus the idea generated by p of x, which is equal to a0 into 1 plus idea generated by p of x plus a1 into x plus idea generated by p of x and so on plus an x plus idea generated by p of x raised to n, which we can write it as b0 plus b1 theta plus b and so on bn minus 1 theta raised to n minus 1. That means that any alpha belongs to k can be written as the linear combination of 1 theta theta raised to n minus 1, and therefore the set 1 theta theta raised and so on theta raised to n minus 1 generates k. So we now show that the set 1 theta theta square and so on theta raised to n minus 1 is linearly independent. We do by contradiction. Suppose it is linearly dependent, then you can always find some elements b0, b1, bn minus 1 not all 0 in f such that the linear combination is equal to 0 in k. That means b0 plus b1 theta plus and so on bn minus 1 theta raised to n minus 1 is equal to 0 in k. So by substituting the value of theta, where theta is equal to x plus the idea generated by p of x, and using the addition and multiplication in the quotient ring, we can write this expression as b0 plus b1h plus and so on bn minus 1h raised to n minus 1 plus the idea generated by p of x, which is equal to 0 plus idea generated by p of x, because the 0 in k is same as 0 plus idea generated by p of x. So this means that this polynomial b0 plus b1h and so on bn minus 1h raised to n minus 1 is an element of the ideal generated by p of x. That means that the polynomial p of x divides the polynomial b0 plus b1h and so on bn minus 1h raised to n minus 1, which is not possible because the polynomial b0 plus b1h and so on bn minus 1h raised to n minus 1 is a polynomial of degree at most n minus 1 and px is a polynomial of degree n. So this division is not possible. Therefore our assumption is wrong. Therefore 1 theta theta square and so on, theta n minus 1 is linearly independent. Therefore, because 1 theta theta n minus 1 generates K and is linearly independent, it forms a basis of K as a vector space over F. Therefore, we can write any element of K as a linear combination of 1 theta theta raised to n minus 1. That means K is equal to set of all a0 plus a1 theta plus and so on n minus 1 theta raised to n minus 1, where ai's r belongs to F. So because the basis contains n elements, the dimension of K as a vector space over F is equal to n. That means the degree of the extension K over F is equal to n. Now K is equal to Fx mod P of x. Now what is addition and how do you do the addition and multiplication of elements in this K? So let a theta and b theta belongs to K, because we can treat a0 plus a1 theta plus and so on n minus 1 theta raised to n minus 1 as a polynomial in theta. So K, the elements in K are of the form a theta, b theta, and these, suppose a theta and b theta be two elements of K, and you can see that its degree will be, if you treat it as a polynomial in theta, its degree will be less than n. So the addition will be definitely the normal addition of polynomials, but the multiplication in K is defined by a theta b theta is equal to r theta, where rx is the remainder obtained after dividing the polynomial ax bx by p of x in fx. Now let us see some definitions. So let K be an extension of a field F, and alpha 1, alpha 2 and so on is belongs to K, be a collection of elements of K. Then the smallest subfield of K containing both F and these elements alpha 1, alpha 2 and so on, which is denoted by F of F round bracket alpha 1, alpha 2 and so on, which is called the field generated by the elements alpha 1, alpha 2 and so on over F. If a field is generated by a single element, that means if K is equal to F of alpha, then K is called a simple extension of F. And the element alpha is called the primitive element of the extension. So now we have seen that the element of Fx mod P of x are the elements of the form a0 plus a1 theta plus and so on an theta raised to n minus 1 theta raised to n minus 1, where ai belongs to F. So now here we are going to show that this field K will be isomorphic to a simple extension of F. So the theorem states says, let F be a field and Px belongs to Fx be an irreducible polynomial, and K be an extension of field F containing the root of P of x. And let F of alpha denote the subfield of K generated by alpha or F. Then we can show that Fx mod P of x, the idea generated by P of x, is isomorphic to F of alpha. Let us see the proof of this. Consider the function phi from fx to f of alpha, where the polynomial fx goes to f of alpha. So this means that if I take any element of f, it will goes to f only. That means it goes to itself. That means that phi restricted to f is an identity map, and phi in fact takes h to alpha. So clearly we can show that phi is a ring homomorphism, because phi of fx plus gx by definition is same as f alpha plus g of alpha, which is equal to phi of fx plus phi of gx, and similarly phi of fx into gx is same as f of alpha into g of alpha, which is equal to phi of fx into phi of gx. Therefore phi is a ring homomorphism. Because alpha is the root of p of x, p alpha must be 0. So which implies that P of x must be belongs to kernel phi. So therefore this map phi induce a homomorphism phi1 from fx mod ideal generated by p of x to f alpha. So because p of x is irreducible and fx is a PID, the ideal generated by p of x is a maximal ideal, and so fx mod, the ideal generated by p of x, is a field. Now, note that this phi1 is a non-zero map because phi1 restricted to f is same as phi restricted to f, which is equal to identity. And we know that phi1 is a map from a field to another field, and it's a non-zero map, therefore phi1 is a injective map. Therefore, fx mod, the ideal generated by p of x, will be isomorphic to image of phi1, and image of phi1 is same as phi1 of fx mod, the ideal generated by p of x. And we can see that this image is a subfield of f alpha, and because alpha is equal to phi1 of x plus p of x, this is belongs to phi1 of fx mod p of x, and therefore alpha belongs to this image of phi1, and image of phi1 contains a copy of f also. So we can think of phi1 of fx mod p of x as a subfield of f alpha containing alpha and f. So therefore, by the definition of f of alpha, we know that f alpha is the smallest subfield containing f and alpha. So therefore, by definition of f alpha, image of phi1 is equal to f alpha. So therefore, fx mod, the ideal generated by p of x, is isomorphic to image of phi1, and image of phi1 is same as f alpha. Therefore, fx mod p of x, the ideal generated by p of x, is isomorphic to f alpha. So that's a proof of it. And if you combine the previous two proofs or previous two theorems, if degree of px is equal to n, then the basis of f alpha or f is what it is, 1 alpha, alpha square, and so on, alpha raised to n minus 1. Because we have seen that fx mod f, the degree of extension of f alpha over f is an extension of degree n, or f alpha is a vector space over f with the dimension n. Now let us see some examples. So the first question is, find the extension of Q in which px is equal to x cube minus 2, which you treat it as a polynomial over Q, has a 0. What is the degree of extension? So because p of x is equal to x cube minus 2, by Eisenstein criteria, by taking the prime number 2, then 2 divides the constant and 2 does not divide the leading coefficient. Therefore, by Eisenstein criteria, p of x is an irreducible polynomial over Q. That means that px has no roots in Q. So the previous theorem says that we can find an extension of Q in which px has a root. What is that extension? That also we have seen in the previous theorem. That extension is the quotient qx mod x cube minus 2. And we have seen that this quotient qx mod, the ideal generated by x cube minus 2, is isomorphic to q alpha, where alpha is a root of x cube minus 2. So let us take one root, alpha is equal to cube root of 2. Then we obtain qx mod x cube minus 2 is isomorphic to q cube root of 2. And what will be the basis of q cube root of 2 as a vector space over q, which is same as 1 cube root of 2 cube root of 2 the whole square, that is same as cube root of 4 over q. So therefore, q cube root of 2 is an extension of degree 3 over q, because we have seen that there are 3 elements in the basis. So therefore, this field extension has degree 3. That means that the degree of extension q of cube root of 2 over q is equal to 3. So here we have taken alpha is equal to cube root of 2 is one root, but note that there are 3 roots for h cube minus 2 in C over complex numbers. They are cube root of 2, omega cube root of 2, where omega is the cube root of unity, and which is same as e raised to 2 pi I by 3, and the other third root is omega square cube root of 2. So therefore, by the previous theorem, we have the quotient ring QH mod h cube minus 2, which will be isomorphic to either we can treat it as q of cube root of 2, or this, in fact, this is also isomorphic to q omega cube root of 2, because omega cube root of 2 is also a root of p of h or h cube minus 2. Also, qh mod, the idea generated by h cube minus 2, is isomorphic to q of omega square cube root of 2. So another example is if f is equal to r and ph is equal to h square plus 1. So you can see that ph is reducible over r. Therefore, fx mod p of h will be isomorphic to r with a root of h square plus 1, which is either I or minus I. So fx mod, the ideal generated by p of h, is isomorphic to ri, r of I, and which is same as c, because r of I is same as a plus ib, where a and b are in R, therefore which is same as the set C. And therefore, because p of x has degree 2, so the number of basis element of C over R is 2, therefore the degree of extension C over R is equal to 2. So for example, if f is equal to q and ph is equal to h square plus 1, clearly p of h is irreducible over q, and so the idea generated by p of h is a maximal ideal. So fx mod, the p of h, the idea generated by p of h, is isomorphic to q of I, where I is one of the root of h square plus 1, and which is same as a plus ib, where a and b are in q. So the degree of extension qi over q is equal to 2 with a basis 1 and I. So another example is f is equal to q and ph is equal to h square minus 2. You can clearly, this h square minus 2 is irreducible over q via isostring criteria by taking the prime number as 2. Then fx mod, the idea generated by p of h, is isomorphic to q of root 2, which is same as a plus b root 2. So the degree of extension q root 2 over q is equal to 2, and the basis for the extension is 1 and root 2. In the next session, we discuss about the algebraic extension. Thank you for learning with cell-based maths capsule. Thank you.